So welcome back, and today we want to look at the chi-square goodness of fit test. However, let's consider the circumstance in which we do not expect the frequencies of the different categories to be equal. So in our previous video we had looked at shift when we are considering product defects here in our fictitious data set, and we're looking at the different shifts, and we assume that the distribution of defects detected in the manufacturing process per shift would be somewhere around the same. The distribution of the frequency would be somewhere around the same. However, today we want to look at that of the defect and consider a circumstance where the distribution is expected to have a claim distribution but not one which they're all equal. So if we go to our variable view and we look, and it's important for you to remember this, right? So the values with 1, or the first values, would represent design. The values with 2 would represent material defects, and the values with 3 would represent process defects. So just remember this order. Design is the first, material second, process third. That is the order in which they come. So these are the different categories that we're looking at. So let us now see how we could do a goodness of fit test. But what if you don't remember what are the requirements or the assumptions? So let's pause to look at that. So remember, the null hypothesis is that the frequency of the count agrees with the claim distribution, and then alternate hypothesis is that the frequency of the counts do not agree with the claim distribution. And the requirements, so if you're using a sample to draw an inference about a population and ensure data is randomly selected, and the sample data consists of frequency counts for each category. So in our example, for each defect category or defect type, ensure that your counts for each and that each category has an expected frequency of at least 5. So now let's return back to our data set. So let's go to analyze, non-parametric, and then you go to chi-square, because the goodness of fit test is a chi-square test, and we're looking at the defect category, and we'll put that in our test variables. Here where it says expected range, get from data, we're leaving that as is. Here now, when it looks at our expected values, they automatically would select all categories equal. But in our example, we want to assume that all categories are not equal. So when we looked at our values, the first value was design, 2 represented material, 3 process. And say, for example, if it's normally expected in the manufacturing process of whatever this product is expected that design defects account for 10% of the defects. So because design is first, we click value. So the first proportion that we want to put in will be that for design. And so for example, if design was 10%, we'd use 0.1, add. The second value was material. And so for example, you expect that normally 40% of defects would be material defects. So the proportion for that is 0.4. And you select add. And the third defect are process defects. And say we expect that process defects normally account for around 50% of defects. So here we'll put 0.5 and you click add. So this would represent for design, this represent the distribution for material, and here the 0.5 will represent the distribution for process. And it's important that you ensure that you put it in the same order in which your values are ordered. Then we click OK. And here we get our output table. So if design defects accounted for 10% of the defects, or observed was 54, then we were expected to see 36.5. For material, it was 40% expected, but our observed was 110, but if it was 40%, it should have been 146. And for process, we expect it to be 50% of the effects, or observed was 210, and therefore expected for 50% to be 182.5. So here we look at the residuals and we can look at the differences, and we could see that the differences in terms of what's observed and expected, they seem to be a bit large. So that is telling us already that it doesn't seem to follow the claim distribution of 0.1, 0.4, 0.5 as expected. And when we look at our p-value, it's less than 0.05. So that tells us that we reject the null hypothesis that states that the distribution would have appeared according to the claim distribution. And this is how you perform the goodness of fit test using PSPP when the outcomes or the frequency of the categories are not equally likely and they have some previously claimed distribution.